Okay, this little video should help you with the waves recap work that you've been set this week. So I'm going to go through each question and kind of try and explain. The video should go through with the questions on your worksheet. So if you kind of keep pausing it and answering the questions throughout, that should help you. Okay, so with the first question, it's just asking you for definitions. Now, a problem with that though, if you just type into Google, so the first word is amplitude. So I just type in amplitude. Okay, now it'll just come up with this, and if you just write the first thing you've got on Google, it's not going to be the right thing. So you want to type in more, something like amplitude definition, and then ideally something like KS3, because that means key stage 3, and that's going to be the definition that you want. And if you go on that, and then maybe go to the first website, and it's you'll find the definition on here somewhere much easier. Okay, especially if you find something like this where you've got a glossary. If you look down here, we've got a lot of the definitions on here that you might need. There's some other ones on here, maybe echo, frequency. So these are the sort of things you want to be looking for. You've got to just actually put some effort into finding something. You can't just type in amplitude and hope the definition is going to pop up for you. So that's the best way to find a definition. Find a website like Bitesize, something like that. Search through there. Okay, you might find the definitions somewhere in there. You might go down, there might be a glossary with some definitions on there instead. So that's how you answer the first question. You need to find the definitions for all these keywords. Ideally, if you know them yourself, write them in and then check them. But if you don't know them, this is an opportunity to go away and find them, but research them properly. Don't just Google it, Google the word and hope for the best. Find something like this, it will really help you. Okay, on to the second part now. So this asks you to label some things and draw some things onto your wave. So first off, it's asking you for the amplitude and the wavelength on this wave. Now, this is a certain type of wave. This here is a transverse wave. Okay. So, transverse wave. And if we wanted to label certain things on this, like we've asked to label the amplitude and the frequency, we need to know what they are first. So you should have got your definition for amplitude and amplitude and wavelength in your first section. And you should have something for the amplitude, like the height of the wave from the midpoint to the top of the peak or the bottom of the trough. So the amplitude could either be from there, because this here is the midpoint, and we have at the top here, that is the peak of the wave, and the bottom we call the trough. So from the midpoint to the peak is the amplitude, so then we would label that bit there, that distance is our amplitude. So you need to have a little line drawn with arrows on it, with an arrow on it at least, showing how tall the wave is, and the word amplitude labelled there as that. Now, the wavelength, you should have something to do with either it'll say from the top of one wave to the top of the next wave, or it might say where the wave repeats itself, and I'll show you what it means by that. Because one wavelength on this wave is from exactly, you have to be really precise with this, the top of one wave to exactly the top of the next wave. Now, if we move that around, we can see it could be the top to the top, or it could be the bottom to the bottom, or it could be the middle of one wave to where it repeats itself in the middle again, and it can go kind of up and down as wherever you want it to. It's always the same length. It's the wave repeating itself. Now, one common thing you do get though sometimes, people get wrong on this, is to say the wavelength is like this, the middle to the middle. It's not, because in this the wave's only got half a wave there. A full wave is where it goes down and up and back to the middle again. But I would say the best place to draw your wavelength is like I did at the start, draw it from the top of one peak to the top of the next peak. That makes it really clear what you're trying to show. And we can label that as the wavelength. Now, the second part of this, talking about the particle movement and the energy, I'm going to come on to that later, and then I'll show you why. But I'm going to go on to the second type of wave now, which is a longitudinal wave. Okay, so we've got a longitudinal wave here, and again we want to label a couple of things on this. So first off, we want to label the wavelength again. Now the wavelength's where it repeats itself. Now this time we've not got peaks and troughs, okay? We've got areas where there's lots of bits squashed together and areas where it's very spread apart. Now, where it's repeating itself is going from one area where it's squashed together to another area where it's squashed together like that. Or, again, this can be any part of it. It could be one area where it's far apart to another place where it's far apart. So you need to draw that on. I'll do it from there and label that as your wavelength. Okay. Now, these areas where I've been talking about them being squashed together and far apart, but you can probably work this out yourself. One of them's called compression and one of them's called rarefaction. So I think for yourselves, I think you can probably work out that the area where it's squashed together is compressed, so we call that an area of compression. You need to label that on yours as well. And in the areas where they're far apart, the particles are rare, so we call it an area of rarefaction. Because the particles are, and I'll highlight that, rare. Okay, so particles are rare, so we call it rarefaction. Particles are compressed, so we call it compression. So this is a longitudinal wave, and this is a transverse wave. Okay, this should go through now the part B of question 2 and part C of question 3, as well as trying to explain how you should answer question 4. So it's a little bit complicated and you need to kind of focus on this because we've got some moving waves here. And what it's asking about is how does the particle move compared to how the energy moves? So for this reason, I've got on here highlighted for you a couple of different particles. And we can have a look in a transverse wave and a longitudinal wave, what the particles are doing compared to what the energy is doing. So just focus on the transverse wave and focus on one of the red particles. How is it moving? And if you look at it, it's moving up and down like this. Now it's not always up and down though. If I put that on its side, it'd be moving side to side. So I can't really say it's moving up and down or side to side because it depends which way around it was. But it's moving this way. And look at the energy. If I'm saying the energy starts here, where does it go? Okay, it goes across the page, kind of this way, doesn't it? Okay, so for this, look at how, now we're comparing them. So we're comparing the particles moving like this to the energy moving across the page like that. And if you look, we've made a certain angle here, I'll call that in blue. So we've made an angle here at 90 degrees. So we've made here a right angle. So we can say that in a transverse wave, the particles move at a right angle to energy. And you see what I mean there? The particles are moving that way up and down, or I could say side to side, or it could be forwards and backwards. But it's irrelevant really, as long as we know that it's a right angle to the way the energy moves. Because if I turn this on its side, it will be the same thing. So that's for a transverse wave. Now, for a longitudinal wave, it's a bit different. If you look at this and try and focus on one of the spring coils, what is it doing? Okay, so say this one here. When the energy goes into it, it goes this way and then goes back. So it's going, the particles in this I've got a label on this as well. So this is your particle movement, and the red line on there, that is your energy. So for the longitudinal wave, the particles are moving like this, okay, forwards and backwards. But again, if you turn that on its side, if I turn that on its side like that, it'd be moving up and down, wouldn't it? So we can't say forwards and backwards or anything like that, because it could be any way really, but it's moving like that, and we can label that on our graph that we've on our diagram we've got. So on there, that needs to be a different colour. We've got our particles moving like this. And the energy this time, so you can see the energy is being put in at the hand here, and it is going across like that. Okay, so the energy is moving across like this. So that is the energy. Change that colour again. Now, again, we've got to compare these two lines. So we've got the energy going across and the particles moving like this. They're not right angles anymore, they're both going the same way. And if you have two lines going the same way, you say they are parallel. So the particles move parallel to the energy. Okay. Now, for question number 4, it asks you to describe the difference between transverse and longitudinal waves. And this is the only difference. You'd say in a transverse wave, the particles move at a right angle to energy. And a longitudinal wave, the particles move parallel to energy. But you want to compare them. So you need to write this yourself in a full sentence, and you need to compare the two. So you need a good comparison word like a however or on the other hand or something like that in there to compare the two. Okay, now we're going to have a quick look at this sort of thing here, which is going to show us what different sound waves look like when you produce them. To try and have a look at things like their amplitude and their wavelength and how they change depending on what the note is. So this is linked to question 5. So looking at the two waves on question 5, there's a couple of differences. Now the first one you might notice is one wave is taller than the other, and that tells us something about the volume of the wave. Because the louder the sound is, so if I put the volume down here as a quiet volume, you'll notice the wave is quite small. If I put the volume up, the wave's taller. So loud, quiet. That's because the louder the volume of the wave, the higher the amplitude of the wave will be. Now the second thing that there is on there is the waves. One of the waves is a lot shorter than the other. It's a lot closer together, a lot more squashed up, and has a shorter wavelength. Now that's to do with what we call the pitch of the wave, and that's the sound if it's high sound or low sound. So if we listen again, a high sound will have a very short wavelength and be squashed up. So a high sound, see, the waves are very squashed together, very short wavelength. Whereas a low sound, the waves are very spread apart. And the higher you go, the more squashed together the waves are and the shorter the wavelength is. Now, last little thing on this, you'll also notice the frequency down here. Now that's how many waves pass by in a second. So if it's got a frequency of 880 Hertz, that means 880 waves in 1 second. Whereas a lower frequency, something down here, this one would have 98 waves in a second. So a higher pitch also means a higher frequency. Okay, now we're going to have a look at light reflecting off a mirror. So you've got a diagram like this for question number 6, and it asks you to continue where the light ray would go. Now think about this. If you shine a a light on a mirror, if you're stood straight in front of a mirror, it will come straight back at you. And that's just like if you throw a ball at a wall. So imagine you stood facing the wall and you throw a ball at it, it will come straight back at you and you'll be able to catch it. But if you throw the ball at an angle, where would it go? So think about that. If this was not like this was a ball and it was going this way, would it go straight back to you? Probably not. It would go somewhere, oh, wrong arrow. It would go somewhere off in this direction here. Okay, and we'd draw a little arrow to show where that would go. Now the reason for that is that whatever angle it hits the mirror at, or whatever angle the ball hits the wall at, it's reflected or bounced off at the same angle. Now that is away from something which we call the normal line, which is this line which we'll represent with a dotted line in the middle. Now the normal line is at 90 degrees to the mirror. Okay, so we'll draw that little angle on there. We've got a 90-degree angle there, okay, as the normal line. Now, we've got a couple more things here. We've got one is the line going in, and that creates something called the angle of incidence. Okay, now that's the angle which it hits the mirror. Okay, and you measure it from the normal line to the line going in. That's the angle of incidence. And you also have, on the other side, the angle of reflection. So we'll draw that on a different colour. So we've got here, down here is the angle of reflection. Now what you'll notice is that the angle of incidence is the same as the angle of reflection. So if we were told that the angle of incidence was 20 degrees, for example, we would be able to say, well, the angle of reflection must also be 20 degrees because they're always the same. Because whatever angle you shine the light into the mirror, it reflects off at the same angle. Okay, so if I decided to make this suddenly much steeper, then it would reflect off much steeper. Think again, go back to the throwing the ball against the wall. If you throw it at a much steeper angle like this, it would bounce off much steeper. And if you throw it at a really shallow angle like this, okay, it would bounce off at a really shallow angle. So that's what always happens. You always get the angle that you shine the light into the mirror is always the same as the way it reflects away from the mirror. If we measure from this normal line, which is an imaginary line, at 90 degrees to the mirror. Okay. So hopefully you should have completed this entire sheet now. If you're not sure, go back through the questions. The video should go in the same order as the questions go. Okay, so go back through the video and go back through the questions if you're stuck. If you're still stuck, obviously contact your teachers and we'll try and help you out as much as possible. Okay, hope everyone's okay, and I'll leave that there.